So how are physics and graphs related? Well, one of the main goals of physics is to take something that happens in the real world and describe it with math. The math then can be better described, or one way to better describe the math is by looking at graphs, and that's our goal here. This is related to the dreaded word problem from your grade school days. How do you take words describing something, turn them into math, and then turn those math description into pictures or graphs? So let's give it a try. Okay, as I said, the goal of physics is to describe some event with simple mathematics. So we'll take a simple event. We have a pitcher standing on a cliff. She throws the ball off the cliff with a horizontal speed of v0. Only horizontal speed. Make it simple. Nothing vertical. The height of the cliff is h, and the ball leaves her hand directly above the cliff edge at a height above the cliff edge of y0. So how do you describe the position of the ball as a function of time? What do? Well, the first step, and which is often forgotten, is you need to decide where is the origin of your coordinate system. Where are you measuring from? Anytime you want to know the position of an object, you have to decide where, relative to what. Am I measuring from the chair I'm sitting in to that object? Am I measuring from the door to that object? Where am I measuring from? So I have to pick a spot. And it turns out there's always a few good ones. In this case, one possibility is we choose a coordinate. That's where the x and y axes cross. That's the origin. Where we choose that origin where the ball leaves her hand. So probably about where it's shown on the picture. The advantage of that is once the ball leaves her hand, the physics is simple. There are no other forces acting on the ball except for gravity. That's the only significant force. Before that, her hand was moving the ball all over the place. She might have thrown it overhand or underhand. We don't know what was happening before she releases the ball. Once she releases it, it's easy. So this is a good choice. An equally good choice might be at the top of the cliff. There again, we're in the same x position where she releases the ball, so no problem with that. And we just have to have an offset of y0 for where the release is. That might be good, or that's another good choice. Or we could choose on the ground, right along the cliff edge, the x-axis right along the surface of the ground, and the y-axis pointing along the edge of the cliff. That's also a good choice. They're all pretty equally good, and you could use any one of them. We're going to choose the last one. Step 2 is when is time equals 0. Sometimes this is so obvious that it gets forgotten. But as we said, that once the ball leaves her hand, the description of it becomes easy because there's only one force that's significant, that's gravity. So we're going to choose the moment of release to be time equal to 0. So moment of release is when we're going to start our clock. Okay, so I've moved the picture and description of the problem up a little bit. We've decided where we're going to have the origin, so we know where x is equal to 0 and y is equal to 0, and also when time is equal to 0. So to describe the position of the ball as a function of time, what do we need to do next? Well, step 3 is to use some physics knowledge. And I will give you this physics knowledge so we can go on and figure out how to make the graphs. Well, the motions of x and y are independent of each other. That means that whatever is happening in the x direction does not affect the y direction motion, or vice versa. An arbitrary position, we're going to call it u of t, that's moving with a constant acceleration a sub u, can be written with this equation. It means that u is a function of time, and u could be x or y or z or something else, that u of a function of time is equal to the initial position u at time 0, that's u sub 0, plus the initial velocity, that's v, that's sub u comma 0, or the initial velocity at time 0, times the time, plus 1/2 times the acceleration in the u direction, a sub u, times t squared, the time squared. So we're going to use this equation to develop equations for x of t and for y of t. There's no acceleration in the x direction. Gravity only acts vertically. And by our choice of origin, the initial position is 0. So x of t becomes very simple. We only have x of t equal to v0 of t. The velocity in the x direction was defined as being v0. That's the initial horizontal speed, and actually it never changes. There's no acceleration, so the velocity can't change. The y direction is a little bit more interesting. The initial position of the ball is y0 plus the height of the cliff, h. No initial velocity is in the x direction. There's no initial velocity in the y direction. All of the velocity is in the x direction. But there is acceleration in the y direction, and it has a value of minus g. We're using g because it's common to use little g as the acceleration of gravity. And the minus means that the acceleration is downward toward the ground. So we can write our equation for y of t as being the initial position, y0 plus h, minus 1/2 gt squared, which is the acceleration term. There's no initial velocity, so that doesn't appear. Okay, so now we have x of t equal to v0 of t. Let's go ahead and plot this. Well, it's the graph of a straight line, so this is the graph of x versus t. So we see that the slope of this line in red is v0, the velocity. It's common that whenever there is constant velocity, the graph of the line as a function of time is going to be a straight line with the slope of the velocity. Okay, y of t is a function of time. It has a constant, y0 plus h, plus a term which goes like t squared, which is a parabola. In this case, the downward facing parabola because we have the minus sign. How wide the parabola is determined by the constant in front of t squared, the 1/2 g. So in this picture, we see that at time equals 0, y has the value of y0 plus h, so it starts there. And as time progresses, it increases like, or decreases like t squared. So it falls like minus 1/2 gt squared from that value. I've stopped it when the value of y hits the ground, assuming, or y equals 0, which is the ground, so it's assuming that the ball can't go through the ground. So one question we can answer is, when does it hit the ground? When is y equal to 0? Well, we can look at that point. We can read it off on the graph if there are numbers there, or in this case, since we have a variety, an algebraic or expression or a symbolic expression, we can solve for that t when y is equal to 0. So we set y of t equal to 0 and solve this equation for t, bringing the y0 plus h to the other side, dividing through by the minus 1/2 g, and then taking the square root, we get that t is equal to the square root of 2 times y0 plus h divided by g. What can we say about the x direction? Well, let's assume the ground is soft. So if the ground is soft, the ball is going to stick in the ground wherever the ball first strikes it. Of course, if the ground was hard, the ball would continue bouncing, and if it's perfectly elastic, it would continue bouncing forever, and x would keep growing. But let's assume the ground is soft and it sticks where it hits. In that case, we know the time at which it sticks, so that the final position of where it sticks is just going to be v0 times that time. So I just plugged it in there. Okay. So now we've gone ahead and shown how you can create, take a simple picture, turn it into math, and then create graphs from it. We're going to let you take a turn at giving it a try in the next problem.